There's pretty good evidence that watching a lot of television can contribute to obesity. Watching TV is a sedentary activity, plus all that food advertising can give you the munchies. Here's some made-up data that show a relationship between hours spent watching TV and percentage of body fat. I'm going to use these data to illustrate how to compute and interpret a basic regression analysis in Microsoft Excel. Let's look at how the data are arranged, how to tell Excel to compute a regression, how to interpret the results, and finally how to check for some possible problems with the analysis. In the data file we have three variables. Column A simply contains an ID number for each person in the dataset. We have a total of 50 people in this particular dataset. Column B indicates the number of hours each person typically spends watching television in a given week, and column C tells us each person's percentage of body fat. So, for example, person 1 typically spends about 19 hours a week watching television and has a 31% body fat figure. Person number 2 typically spends 27 hours a week watching television and also has a 31% body fat figure, and so forth, on down to case number 50. Now here's how to get Excel to give us a regression analysis. Begin by choosing the Data tab and coming to Data Analysis and clicking that, and then looking for Regression on the Data Analysis menu that pops up. Choose Regression and click OK, and up comes the Regression dialog box. Now you need to think about which variables you want to put in the input Y range and the input X range box. The convention is to put the cause on the X range and the result on the Y range. So our sort of working theory here is that the number of hours you spend watching television causes, or at least has something to do with, your percentage of body fat. So let's put weekly TV hours on the X range and percent body fat on the Y range. Here's how to do it. Let's start by clicking in the input Y range box and then highlighting our result, which is the percentage of body fat information in column C. Just click and drag with the mouse all the way down. When you get to the bottom, let up. Now click in the input X range box and do the same for column B. Notice that I'm including the column headers as I do this. That's so that they'll show up in the output as labels. Okay, so there's our data range highlighted. Because we included those column headers, be sure to click the labels box. This tells Excel that the first entry in every row is a label, not a number. And then let's choose for our output range an area right next to the data we're dealing with. This is just a preference of mine. If you choose the default, it'll put the output on a different tab, which is also okay. I'll put it right here in cell E1. And finally, under the residuals, click the line fit plots right there. Make sure that button is checked. And now we're ready to go. Go ahead and click OK. Once you click OK, Excel gives you a whole bunch of output. And it's kind of complicated. There's a lot to look at here. Let's begin by looking at the graphic that we asked Excel to produce, the line fit plot. I'm just going to select it here and stretch it out a little bit so we can get a better look at it. Okay, if you're trying to understand what goes on in regression, this is a good place to start. You see two colors of dots on this chart. There are blue dots and there are red dots. The red dots are arrayed in a straight line. The blue dots represent the individual cases in the data file. So each blue dot is one of those 50 people who were in our data set. For example, this dot right here represents somebody who watched about 50 hours per week of television and had a percent body fat of just under 35%. This person here is kind of at the opposite end of the spectrum. This is a person who watched somewhere between 0 and 10 hours of television a week, probably about 5, and had somewhere between 10 and 15% body fat, looks like maybe about 12%, something like that. And everybody else, notice, is kind of arranged somewhere in between. So each of the blue dots is a given person. The red dots, which are on a line, form a line that you might think of as the trend line. Statisticians would call it the regression line. And basically it's It's the one line that you could draw through all of the blue dots that is simultaneously as close as possible to each one of the blue dots. So it kind of represents the whole group of blue dots. It also kind of tells you the direction and the nature of the relationship between watching television and percentage of body fat. Notice that as the number of hours spent watching television each week increases, so does the percentage of body fat. So you've got individuals here on this end of the scale, on this end of the spectrum, who don't watch a lot of TV. They also seem to tend to have lower body fat percentages. Whereas the folks on this end of the spectrum tend to watch a lot of television and also tend to have fairly high percentages of body fat. So there's a linear relationship between weekly TV hours and percentage of body fat, and that's what that red line is telling you. It's telling you that generally as weekly TV hours increases, so does the percentage of body fat. Now with different data, this line could look different. It could, for example, start high on the left and trend downward as you move from left to right. That would indicate a negative relationship between whatever's on the x-axis, the horizontal axis, and whatever's on the y-axis. In other words, if such a line represented the relationship between weekly TV hours and percentage of body fat, it would be telling you that the more television you watch in a given week, the lower your percentage of body fat is. We would call that a negative relationship. As one goes up, the other goes down. It would also be possible for the red line to be more or less horizontal. That would indicate that there was really no relationship between weekly hours spent watching television and percentage of body fat. In other words, it would indicate that it doesn't matter how much television you watch in a given week, your percentage of body fat is about the same as everybody else's. Now let's think about how the blue dots relate to the red trend line. Look, for example, at this dot right here. This is a person who watches about 10 hours of television a week and has about 10% body fat. Now, based on the overall trend, we would expect this person to have more like 15% body fat. In other words, we would expect them to be right, that's where they would be if they were right here on the trend line. So there's a little bit of difference between the characteristics of this individual person and the overall trend. That difference is called the residual. The larger these residual differences are, the weaker the relationship is between weekly TV hours and percentage of body fat. The smaller those residuals are, the stronger the relationship is between weekly TV hours and percentage of body fat. So now let's look at how these numbers over here to the left relate to the chart we just looked at. Let me scoot over a little bit. Now to get these columns to stretch out, again, just highlight the columns that have data in them. Float your cursor between any two of those columns and double-click. And the columns will stretch out to show us everything that's in there. Alright, the very first place to look in the output is right here. This is the column where we will find the p-value, the probability value, for the variable that we're looking at, weekly TV hours. This is the number that you want to be 0.05 or less. A number that's greater than 0.05 here indicates that there's a pretty good chance that the relationship that showed up could have showed up purely by randomness alone, and that there's nothing systematic going on between the amount of time you spend watching television and the percentage of body fat that you have. In this case, we have a value that's quite a bit less than 0.05. Again, we have some scientific notation here. So we have 0 point and then 9 zeros to the right of the decimal point, and finally in the 10th decimal place there, 473816. This is, again, a very small number. That means there's not a lot of chance that this relationship would have shown up purely by randomness alone. So the alternative is that there's something systematic going on that links weekly TV hour watching to percentage of body fat. So that's the first place to look. This figure here is the multiple R. This is a number that's going to range anywhere from -1 to +1, and it can also be 0. A -1 would indicate a perfectly negative correlation. If you think back about our conversation about how that red trend line can either start high on the left and end low on the right, or it can be flat, or as pictured here, it can start low on the left and end high on the right. Those those are kind of the three extremes of that R value. An R of -1 would indicate that the red line, the trend line, is high on the left, low on the right, and that every one of those blue dots is lined up perfectly on the red line. In other words, there are no residuals, and you have a perfect negative correlation. Now, an R of 0 would indicate that the line is flat or very nearly flat, and that the blue dots are arrayed in kind of a random scattershot pattern around the red trend line. So you have very large residuals overall, and you have really no discernible relationship between weekly TV hours and percentage of body fat. An R of +1 would indicate a perfect positive correlation. In that case, the trend line would look like it looks like here, starting low on the left and finishing high on the right, plus every one of the blue dots would be perfectly lined up on the red trend line, indicating again no residuals, a perfect correlation, but this time a positive correlation, indicating that as one variable increases, so does the other. So those are kind of the three possibilities for that multiple R. R square is just multiple R times itself, squared. And you end up with something we call the percentage of variance explained. So here, R square means, an R square of 0.557 means that the amount of time you spend watching television is capable of explaining or predicting about 55 to 56% of the variation in your percentage of body fat. The adjusted R square is just the same figure, the R square figure, adjusted for the size of the sample. Bigger samples are more accurate and predictive and powerful than smaller samples are generally. The last couple of figures I want to draw your attention to are these right here, the ones in the coefficients column. I've scooted the graphic over so we can kind of put these two side by side and see how they relate to each other. Suppose we have a person who tells us he spends about 10 hours a week watching television. To estimate that person's percentage of body fat, we could do this. We could take the 10 hours a week that he says he spends watching television, multiply it by this coefficient right here, the 0.48, and then add to that the intercept, 10.95. If you think back to high school, you might remember this formula, y equals mx plus b. It's the formula for a line. You probably encountered this in algebra class. That's exactly what we're doing here. Y is the value on the y or vertical axis, in this case the percentage of body fat. M is what you probably learned is the slope. That's the coefficient here for weekly TV hours, the 0.48. X is the value on the x or horizontal axis, in this case the number of hours spent watching television. And B is the intercept, the point at which the trend line crosses the y or vertical axis. So to figure out the value on y, percentage of body fat, you take the slope, 0.48, multiply it by the x value, in this case 10, and add to it the intercept, 10.95. And you wind up with this particular person's predicted percentage of body fat. Now that doesn't mean that's the exact percentage of body fat that person will have, but it is the best guess, the best estimate of that person's percentage of body fat based on what we know about the overall relationship between time spent watching television and percentage of body fat. Another handy use for the slope, remember here it's this 0.48, is to indicate how much whatever is on the y-axis changes each time whatever is on the x-axis changes. So in this example, each time a person's typical weekly time spent watching TV increases by 1 hour, we can expect the person's percentage of body fat to increase by 0.48 of a percentage point, or about half of a percentage point. Now let's look at some of the things you need to check for in order to avoid getting fooled by the results of your regression analysis. Most of the problems in regression can come from something called outliers. These are cases in your data that don't conform to the overall pattern. And they can cause two kinds of problems. First, they can cause you to not see a pattern that really is there. Secondly, they can make you think there's a pattern there when there really isn't one there. Let's look at an example of each situation. Click first on the Data with Outliers tab 1 down here at the bottom of the spreadsheet. And here in columns A, B, and C, you see exactly the same data that we just finished analyzing on the Data tab, but with 6 additional cases added on to the bottom here. And these 6 additional cases are quite unusual compared to the rest of the cases. For example, remember the first column here is the number of hours spent watching TV in a given week, and the second column is the percentage of body fat. We've generally seen that the more TV you watch, the higher your percentage of body fat. But in these cases, that's not the situation. Here's somebody, for example, case 51, who spent 60 hours a week typically watching television and has only 9% body fat. Wouldn't that be nice? And here's a person who only spends 3 hours a week watching television but has 48% body fat, quite high. And the rest of the cases are similarly unusual or different from the overall pattern that we saw. So if you look at these on a scatter plot, like the one that we produce when you click the fit line plot, you see something like this. Here are our 3 cases that are unusual in the sense that they don't watch a lot of television but have relatively high percentages of body fat. And here are the 3 cases that are unusual in the sense that they watch a lot of television but have very low percentages of body fat. Now what happens when you include these 6 cases in the analysis is that, remember, the fit line is trying to represent all of the blue dots as well as it can. So it winds up kind of flattening out to represent both these 3 extreme cases and these 3 extreme cases. And as that line flattens out, the R value begins to drop. It begins to approach 0. Because, first of all, it's not as steep as it was before, and also there are greater residuals. Remember, the residual is the amount of distance between each of the blue dots and the red trend line. So these cases here and these cases here, these extreme cases, all have rather large residuals. The multiple R has dropped to 0.08, and the R square is down to about 1%. The probability value is up to 0.549, or basically 0.55, well above 0.05. So if you just looked at these numbers, you would conclude that there is no significant relationship between the amount of television you watch and your percentage of body fat. But if you scroll back over to the line fit plot, you see that what's really going on is that for most people, there's a strong positive relationship there. But for these 6 individuals in the sample, there's something else going on. For them, the pattern doesn't hold true. They are some kind of an exception to the rule, but the rule is still there. So if you don't check for these outliers, you can end up being fooled by your regression output. Let's look at another way in which outliers can cause problems in regression analyses. Click with me on the Data with Outliers 2 tab right here. And here in columns B and C, we again have data for weekly number of hours spent watching TV and percentage of body fat. But in this case, these numbers were randomly generated. I just made them up. So there should be little or no correlation between columns B and C. But at the very bottom of the columns, the very last case, I've included one person who supposedly spends 99 hours a week watching television and has a 99% body fat rating. So this person is going to be kind of unusual, to say the least, compared to everybody else. In fact, if you scroll over a bit, you'll see a line fit plot of what this is going to look like. So these blue dots down here are everybody else. And this blue dot right here is that one person with the 99 on both values. Now remember that the trend line tries to represent all of the blue dots as best as it can. So this one lone blue dot out there all by itself is going to kind of stretch the trend line out in a way that's artificial. And that stretching out can produce the appearance of a linear relationship when in fact there really isn't one. If you go back to the numbers and see what this looks like, you can see here the multiple R is back up to 0.61. The R square is about 37 or 38% of the variance explained, and the significance level is well below 0.05. So looking at these data, even though we're talking about, in this case, a correlation between two randomly generated columns of numbers, looking at this relationship, you would assume that there is a pretty strong linear relationship here, when in fact there really isn't. All of the linear relationship that is there is due to that one weird outlier case. Now, cases like this aren't that unusual in that, for example, 99 is a fairly common code that the data entry people use to indicate a case that is somehow unclassifiable or a case for which data are missing. Now, those kinds of cases are supposed to be flagged and eliminated before data analysis, but sometimes they sneak in anyway. Sometimes a data entry person can simply hit the wrong key when they're keying data in. All sorts of things can happen, so you just need to be sure you look for these. Watch what happens to the correlation when we delete the outlier case. I've got a chart here, just down below the actual line fit plot, that shows what happens if you delete that 99-99 case. Notice how much flatter the trend line has gotten, and how more rounded and sort of scattershot the pattern in the blue dots is. This is what the relationship between the randomly generated data looks like without that unusual 99-99 case. As you can see from the little summary box here, the R-square has gone down to 0.029, or about 3% of the variance explained, and the p-value is all the way up to 0.2024, well above 0.05. So in this case, an outlier has fooled you, perhaps, into thinking that there's a relationship there when in fact there really isn't one. Now, there are lots of ways to check for outliers, lots of different techniques, and more complicated techniques become necessary as your regression analysis gets more complicated. That is, it involves more cause-type variables. But if you're just looking at a regression between two variables, as we are here, really this line fit plot is going to identify all the outliers that might cause problems. Just look at that line fit plot and look for cases that are all by themselves. Like here, if you had looked at this line fit plot, you would see that one blue case or maybe a couple of blue cases out there all by themselves, and you would recognize them as outliers and deal with them in some way. Back on the other example we had, you could look at this line fit plot and see that you've got those two groups of cases that are again kind of way off by themselves, bucking the trend, if you will. Finally, let's look at how you can know when it's appropriate to do a regression analysis. If you think about the analysis we just did, how many variables were involved? Well, there were two. There was number of hours typically spent watching television, and there was the percentage of body fat. So we have to follow the two-variable path here. Now, what about the measurement level of each variable? Well, the first one, number of hours spent watching television, that's measured on a continuous scale. You know that because the number of hours spent watching television can be put in a sequence from lowest to highest, and also the amount of time between any two adjacent points on the scale is the same. In other words, the amount of time between 1 hour and 2 hours is the same as the amount of time between 2 hours and 3 hours, and between 3 hours and 4 hours, and so on, all the way up the scale. Likewise, percentage of body fat is also continuous. Again, you know that because you can put the percentages in a meaningful sequence from lowest to highest, and the distance between any two adjacent points on the scales is the same. The difference between 1% body fat and 2% is the same amount of body fat as the difference between 2% body fat and 3%, and so forth. So in sum, we have two variables in the analysis. They're both measured continuously, so we know we need to do a regression.